So, today we will discuss infinite series of real numbers. We have already discussed the sequences and various concepts regarding the sequence. So, today we will talk about the infinite series. We define normally when we say if a set of element x 1, x 2, x n are given a sequence, when they are added or subtracted and put it in the form of x 1 plus minus x 2 and like this, then we call it a series. But that is not a authentic way of defining the series, because it does not show anything whether the limit convergent or divergent, whatever. So, we define the series as follows: if x, which is a sequence of real numbers, x n is a sequence in R means set of real numbers, then the infinite series generated by x is this terms sequence x n is the sequence S of partial sum x k defined by S 1 is the first term, say x 1, S 2 is the sum of the first term, that is S 1 plus x 2, S 3 is S 2 plus x 3 and so on. So, S n will be or S k will be S k minus 1 plus x k, that is x 1 plus x 2 plus x 3 up to x k. The number x k, the numbers x k or x n, these are called the terms of the series and the number s k are called partial sums, partial sums of this series. This S k is sum of the first k term of the series and so on. Now, if the limit of S, that is the limit of S k when k tends to infinity, if this limit exists, then we say the series is convergent. And has the sum S. We denote the series as sigma x n is 1 to infinity if first term is x 1, or sometimes we also denote like x n without the suffix, that shows that summation is taken from 1 to infinity. So, this is the way of defining it, or some other, if the first term is starting from x 0, then the summation will be taken from 0 to infinity and like that. And if the series whose first term is say x 100, then the series will start from n equal to 100 to infinity. So, that way we can identify them. Okay. Now, if this limit does not exist, then in that case we say the series diverges. If the limit S k when k tends to infinity does not exist, it means either it is infinite plus infinity or minus infinity or has a various limits does not exist, then we say then we say the series sigma x n 1 to infinity diverges. Okay. So, that is the, for example, we have a series, suppose we have the series sigma r to the power n, n is 1 to infinity. Now, we that is the series 1 plus r square and so on plus r to the power n like this. So, this is the series. Now, we claim if mod of r is strictly less than 1, then series converges. And the sum of the series and sum is equal to 1 over 1 minus r. Sum will be this. But if r is equal to 1, if r is mod r is greater than or equal to 1, then the series diverges. The proof is very simple. Solution. Let us find the first sum of the first n terms. So, let S n is the sum of the first n terms 1 plus r square plus r to the power n. This is the sum of the first term r n minus 1, because this will be first term, second and up to n terms. Okay. Then if I multiply this by r, then what happen, r times S n, this is equal to what, r plus r square plus r n minus 1 plus r n. Now, is subtracted. So, this implies that 1 minus r S n, when it subtracted, it get cancelled in that, and we get finally 1 minus r to the power n. So, what we get it is S n becomes 1 by 1 minus r to the power n over 1 minus r. Okay. So, consider mod of S n minus 1 over 1 minus r, that is equal to mod of r to the power n over mod 1 minus r. Now, r I am choosing fixed, but it is less than 1. If it is less than 1, this term will go to 0. So, this tends to 0 as mod r is strictly less than 1. Therefore, the limit of this S n as n tends to infinity is exist and equal to 1 minus r. So, this series converges and converges to the sum 1 over 1 minus r. For r is equal to 1, obviously, the terms are 1 plus 1 plus 1 and so on, so up to S n will be n. So, when n is infinity, limit S n will tends to infinity. So, it will diverge. For r greater than 1, we will see in due course that it also diverges. In fact, it will limit will not exist and it will go to infinity. So, that we will come and obviously, we can find out the sum. Clear? So, this is very interesting one. Similarly, another examples, this part we will take up after going for the further tests, then we say automatically by pth test it will come diverges. And then let us take this sum, this series sigma 1 over n plus 1, n is 1 to infinity, we claim this converges and sum is 1. The solution is again simple. if I take the terms S n, what happened? This term are S n are 1 over 1 into 2 plus 1 over 2 into 3 plus 1 over up to say n is 1 into n plus 1. So, this will be, if we write it in the form, since 1 over k plus 1, we can break up and put it in the form of 1 over k minus 1 over k plus 1. So, using this, each term we can put it in this way, and once you put it this thing, then S n becomes, this is 1 over 1 minus 2, that is 1 over 1 minus 1 by 2, this will be then 1 by 2 minus 1 by 3, like this 1 by n minus 1 by n plus 1. So, get cancelled and finally, you are getting 1 and 1 minus 1 over 1 plus. So, S n becomes 1 over 1 minus 1 over 1 plus n, all n plus 1. Now, as n tends to infinity, it goes to 1 minus 0, that is goes to 1 as n tends to infinity. This term will go to, as n tends to, this will go to 0 and this is 1. So, the limit of this exists and equal to 1. So, this way we can identify that. So, these are few examples. Now, in case of the convergence series, there is a necessary condition that if a series is convergent, then its nth term will always go to 0. That is a necessary condition for us. So, if a series whose nth term does not go to 0, the series cannot be a convergent series. So, that is the criteria which we have, the necessary condition, for convergence of this series sigma a n is 1 to infinity. So, this we will put it in the form if the series sigma x n, we are doing with x n. So, let us put it x n, sigma x n, n is 1 to infinity, converges, then limit of the x n must go to 0. Limit of x n as n tends to infinity will be 0. That is, any term will always go to 0. Okay. So, of proof, let us see the solution or proof. So, what is our S n? S n basically x n, this is nothing but what? S n minus 1, because S n is the sum of the first term, where S n stands for x 1 plus x 2 plus x n. So, S n minus 1 means up to x n minus 1. So, when you subtract, you are getting S n. Now, this series is convergent. So, limit of the S n will exist. So, limit of S n and limit of S n minus 1 will be same. So, therefore, limit of x n when n tends to infinity, this will be the limit of S n minus limit of S n minus 1, but both the limit will be the same. So, it will come out to be 0. So, this is the necessary condition for a series to be convergent, but this is not a sufficient condition, but this is not remark, but this is not a sufficient condition. That is, if at any term of a series converges to 0, then it may or may not be a convergent series. For example, suppose I take this series sigma 1 by n, n is 1 to infinity. Here x n is what? 1 by n, which tends to 0 as n tends to infinity. And this we have seen that this series and but the series S n, the series sigma 1 by n 1 to infinity diverges as we have seen earlier, because it is a harmonic series. In fact, the proofs we have gone already seen, because the if you remember, we got the S n to be 1 plus 1 by 2 plus 1 by 3 up to 1 by n, is it not? And then it keeps on increasing. When you take the n, then it keeps on increasing. In fact, limit of S n will go to this keeps on increasing, okay, diverges. So, this we have already increasing functions like this and keeps on like unbounded one. So, this we are not already shown in the first lectures while going for this series sequences. In case of sequence, this example we have taken and shown the series diverges. So, here this diverging. If we take another example, say sigma of 1 over n square 1 to infinity. Now, here the x n which is 1 by n square goes to 0 as n tends to infinity, but this series converges. What this series converges, that will also be shown in the next few after few article to be covered. When test for the series is there, then this is 1 upon sigma n to the power p type, where p is greater than 1, series will converge. So, that we will prove it, hence from there you can say this is convergent. But what is the day? You see that these two series, in both the series the nth term goes to 0, here also it goes to 0, but one series diverges, other converges. So, the taking the sequence x n, the nth term, checking whether it is tending to 0 or not, this will not give a conclude either. Just tending to 0 will not imply the series is convergent, because it may be divergent also. However, if we take any sequence x n, any series x n whose nth term does not go to 0, then series has to be a diverging series, because if it is convergent, then correspondingly the nth term must go to 0. Okay. So, that is why here this will third point remark, if in the series sigma x n 1 to infinity, the nth term of positive term sigma x n a series, if the x n is a sequence of terms, if the limit of x n when n tends to infinity does not tends to 0, then the series diverges, then the series sigma x n 1 to infinity diverges. And the reason is very simple. The reason is why, because if it is convergent, then according to the necessary result earlier, the necessary condition for a convergence of the series, the nth term must go to 0. So, this is not happening, therefore, it will diverge. So, if the series of positive term, let us take the positive, because the series of positive terms also positive terms, okay, where this goes. So, this was part of it. Okay. Now, there is another result, just like a Cauchy convergence criteria. We have a Cauchy convergence criteria for the sequence. Any sequence of real number is convergent if and only if it is Cauchy. That is, it satisfies the Cauchy convergence criteria, that after a certain stage the difference between any two arbitrary terms of the sequence is less than epsilon, given epsilon, then we say the sequence is convergent. So, correspondingly we also have a result for a series, that is known as the Cauchy convergence criteria for series. So, next is Cauchy convergence criteria for series. The result is the series sigma x n 1 to infinity converges if and only if for every epsilon greater than 0 or for given epsilon greater than 0, there exists a positive integer n, there exists a sequence as there exists a positive integer capital M which depends on epsilon such that for all m n greater than or equal to capital M, the following condition holds: the mode of S m minus S n, the partial sum of the series mth term up to mth term and up to nth term is less than epsilon for all n. That is equivalent to say is that mode of x n plus 1, if I choose m is greater than n, if m is greater than n, then x n plus 1, x n plus 2 up to x m is less than epsilon. That is up to here. So, this is known as the Cauchy convergence criteria, and this part is if and only if, that is if the series converges, then sequence of its partial sum will satisfy this condition. Clear? And obviously, we have defined the convergence of the sequence as when the limit of the Sm goes to limit exists. So, when the limit of the sequence of partial sum exists, then only we say the series converges. So, suppose the series converges. So, limit of Sn exists. It means the limit of Sn exists means it must satisfy the Cauchy convergence criteria. So, this is nothing but the Cauchy convergence criteria. And conversely, if this is true, then the limit of the sequence Sn must exist. Limit of the sequence Sn exists means this series must be a convergent one. So, that shows the connectivity. Okay. Now, based on this, we have a very interesting results. The result is in the form of theorem. Let x n be a sequence of non-negative real numbers then the series sigma x n 1 to infinity converges if and only if the sequence of partial sum S of partial sums sequence S of Sk of partial sum is bounded. Okay. And in fact, when it is bounded, the limit superior of this limit of Sn will come out to the sum of this. So, let us see the proof of it. Okay. What is given is the sequence x n is a sequence of non-negative real numbers, positive numbers, okay, non-negative maybe 0. The series is convergent if and only if the sequence is of the partial sum is convergent. So, suppose the series converges, it means limit of the Sn will be exist. And what is our Sn? Sn is basically the partial sum. S1 is the first term, S2 is the sum of the two terms 1 and 2, and since x1, x2, xn are non-negative real numbers. So, maybe few may be 0 or maybe strictly greater than 0 also positive number. So, S1 definitely less than equal to S2, which is less than equal to S3, and so on like this. So, what we are getting is the sequence of the partial sums. So, the sequence of partial sums sequence of partial sums is a monotonic sequence of increasing numbers, increasing monotonic sequence increasing monotonic sequence of real numbers. Okay. Now, what is the monotonic convergence theorem? Monotonic convergence theorem says any monotonic sequence which is either increasing or decreasing, and if it is bounded, a monotonic sequence which is increasing and bounded above, then it must be convergent, or monotonic sequence which is decreasing and bounded below must be convergent. Here this is a monotonic sequence, increasing sequence of real numbers, and what is given is a series is convergent. If this sequence is given to be bounded, suppose I take this part, if sequence is bounded, then it means this monotonic sequence is bounded. So, once it is bounded, it has to be convergent. Okay. So, if the sequence S k is bounded, then by monotone convergence theorem, the sequence S k is convergent, that is limit of x k exist. In fact, it is the upper bound for this. It is the supremum value of all s k's when the k belongs to integer. Supremum value, it is upper bound for this. We have not discussed upper bound, we will take up after that. Okay. In fact, this limit. So, if the s k is bound, partial sum is bounded, then we can immediately say by monotone convergence theorem, this limit will exist, hence the series is convergent. So, this implies the series sigma x n 1 to infinity converges. Conversely, if given the series sigma x n 1 to infinity converges, it means what? That means the limit of this sequence S k over k exists finite. Now, every convergent sequence is a bounded sequence. So, this means that sequence S k is convergent. So, it is bounded. So, this proves the both way, that if this series is convergent, then the sequence of the partial sum will be bounded sequence, and vice versa, if sequence of the partial sum is bounded, then the corresponding series will be convergent. So, that is the convergence criteria for that.